Gold is viewed as an immensely valuable resource, recognized even from the ancient times as valuable. But in 1911, its value showed itself in a big way. Ernest Rutherford's gold foil experiment used one piece of gold foil to change how the world viewed matter. I'm Ben, welcome to Physics or Bust. To understand the significance of Rutherford's gold foil experiment, we have to go back before he published his paper in 1911. And so in the 1800s, most people were going by Dalton's view of the atom, which was that every atom was a solid piece of material. And that view stuck for about 100 years until in 1904, J.J. Thomson, who was a former teacher of Rutherford, published findings leading to the plum pudding model. He had done an experiment with a cathode ray tube where he was able to get electrons coming off these metal pieces, and then they were attracted to a positive plate and repelled from a negative plate. So those particles that were coming off had to be negatively charged. He figured out that they were way smaller than hydrogen, which was the lightest element. So he put forward a model that you had this massive positive charge spread throughout the atom, and the negative charges were kind of sprinkled around like plums in a pudding or chocolate chips in a muffin. And J.J. Thomson's model for the atom was only proposed a couple of years before he did these experiments, so it wasn't even widely accepted as a model for the atom yet. In 1899, Rutherford demonstrated that there's at least two types of radiation coming off of radium. So he figured out that the alpha particles, so he called them, were positively charged and very massive compared to the beta particles, which were negative. And they later figured out that those beta particles are actually high energy electrons, and the alpha particles are actually helium nucleus. So they're two protons, two neutrons together. But at this time they didn't know that. All they knew was it was a positively charged particle with some really fast energy. In 1908, he had Hans Geiger, one of his students, do an experiment where he had radium on one end, a glass pipe about 2 meters long, and a screen on the other. And then right in the middle, he was able to put a film. And that screen on the very end was coated with zinc sulfide or zinc sulfate, one of the two. And what that did is when the alpha particles hit it, it would give a small flash of light. So then he had a microscope that he attached to it so he could actually see the light. And he sat there watching it. And the idea of that experiment was to count how many alpha particles are coming off this radium, and that way they kind of had an idea of how radioactive radium was, how many particles were coming off, and they figured out there was about 80 per minute. Hans Geiger did the experiment counting the number of flashes that came through. So it's not all that surprising with how tedious that work was, that he's the guy that figured out a machine to do the counting for you. But what they also figured out was if they put air in there, or they put a thin piece of metal in there, that instead of all the alpha particles coming and hitting right in the center, they would be slightly deflected one way or another. So then Hans Geiger asked Rutherford, can we do an experiment that we look at how big the deflections are? And so Rutherford said, great idea, well, let's set it up. So then the question comes, how do you set up an experiment where you can have these alpha particles shooting and see all the way around and figure out and measure the angles of deflection? So what they did is they made a long strip of film that had that zinc sulfide on it so that you could make a circle. And they already had their radium source, so they could put that on one side so that it would shoot out a stream of alpha particles. And then they took a really, really thin piece of gold. So thin it was 0.00004 centimeters thick. 0.00004 centimeters thick. That is incredibly thin for the time. We can get them thinner now, but in 1900, that was incredibly thin. It really is only about 1,000 atoms thick. So they had what they needed. They had a radium source. They put the gold foil right smack dab in the middle of a circle of the film that's coated with zinc sulfide, so that they'll get a flash anytime it hits that film. And then what they had to do was sit, watch, and wait. So, helping Ernest with the experiment were Ernest Marsden and Hans Geiger, two students of his. So they sat and essentially kept watching and watching and watching, recording the angles that they kept seeing flashes and how many of them that they saw. But when they started, and when they actually saw a flash that was greater than 90 degrees, that was just mind-blowing. They never expected to see one at that angle. When they were doing this, they could only look, because of the setup they had, they could only look at one angle at a time. So they had to, because it was an enclosed container, so that they could pump out the air, not have any air affecting the alpha particles going through. And so then that screen had to be viewed from a really small hole with a microscope attached, and they could shift that around and look at it. They couldn't just be standing above it and look down and be like, oh, yep, I see a flash over there, I see a flash over there. They had to look at one angle, see how many were coming. Another angle, see how many were coming. And so with the straight on, no deflection, there were hits consistently, right? Most of them were in that zero deflection. Maybe a little deflection here or there was pretty common. But when they got to larger angles, they sat and they waited and waited. And by the time they got around to the ones that were really startling, where they actually hit and bounced back, there literally would have only been about 1 or 2 every 8 hours. So in a whole day of looking, they would have only gotten 2 flashes. That is some serious patience. So he's doing this, and his thinking was that it would be one more experiment to confirm J.J. Thomson's model. In fact, reflecting later, Rutherford said it was almost as incredible as if you shot a 15-inch shell at a tissue paper and it bounced back at you. And part of the reason he was so shocked was that he had done calculations to figure out how much deflection he should expect. And when that calculation was so far off, he figured out that the charges had to come so close together so that that force was was great enough to actually change the direction of the alpha particles and get it turned back the other way. But it had to be so dense that it was 100,000 times smaller than he had thought. That's a big number. And to put this in perspective, if you took a grain of sand as the nucleus, where all the positive charge was located, how big would the atom have to be in order to be 100,000 times bigger? So 100,000 times bigger would mean that it'd be at the center of a professional league football stadium. Grain of sand, it has all the mass, so what's in the rest of it? A few electrons spinning around, and the rest of the space is just empty. So when Rutherford published in 1911 that he had done this experiment with the gold foil and shown that the positive charge really must be all concentrated at the center of the atom, it was a huge change to the atomic model. Now, instead of atoms taking up all that space, all the mass was concentrated in one tiny little spot in this huge expanse of space. So when we think about walls, this is almost all empty space. My hand is almost all empty space. 99.9999999, might be another 9 in there, percent of this mass is just empty. There's nothing there. It's that little bit of space that actually has material that keeps us from just bye. So the model of the atom Rutherford proposed was, instead of having just a big massive positive charge with electrons scattered throughout, all that positive charge was going to be concentrated in that little grain of sand in the center of the football field, with electrons going in nice orbits around. That's the only way that he could think of that they would not fall into that positive charge, was that they had to be moving around in orbits. So with this new model of the atom and all that empty space, the question comes, why can't my hand go through this wall? Most of it's empty space anyway, both my hand and the wall. We'll look at that on another video. Don't forget to like and subscribe. We'll see you on the next video.